So can everybody see the main page? So Stratasys Technology and Applications Overview?
Yep, that's perfect, Martin.
Great. So kicking off, I'm Martin Kirk, product specialist for laser lines, and today I'm going to cover the Stratasys portfolio of technologies and applications that become available on each platform. So there are now 5 technologies within the Stratasys portfolio. You've got PolyJet, which is obviously Object originally, stereolithography, which was RPS, industrial FDM. You've now got Origin P3, which is DLP printing, and now we've also got SAF, which is selective absorption fusion, which came out last year. So I'll dive straight in with FDM. So this is Packline Limited using Ultem 1010 resin, which is certified for food contact in the European Union. This application is a food packaging feeder and also a push coffee capsule packaging machine, where there were cost savings of up to 55% with shorter lead times versus traditional methods. With the benefits of AM design freedom, as of today, these parts have surpassed 6 million cycles in production. Switching materials to Nylon 12CF. This is Rocky Mountain Chocolate Factory. They're printing end effectors for lifting wrapped chocolate bars. The existing metal part was malfunctioning, so they need replacements with faster lead times. So they switched to Nylon 12CF, reducing machine downtime, and they can print spare parts on demand, and it was a cost saving. This is Eckhart, develops automation tools for Ford, again using Nylon 12CF to replace metal components, but they also use ASA for simple non-structural jigs. Solution is lighter and cheaper than machining, and it's great for end-of-arm tooling because of the weight savings. This is a nice example from one of our customers. Hopefully, is the video running, Nancy?
I can see it running, Martin.
Yeah, great. Yeah, this is a nice example from one of our customers. It's form automation, so pick and place. So the challenge was to improve the existing process for end-of-arm tooling. So basically, the gripper fingers were bending out of shape. You had small loose parts which could possibly fall into the food trays, and the components were manufactured externally. So the solution was additively manufacture 2 components, a 92 short A that's printed via FDM, and then as a spring, and then a blue ASA frame. The assembly reduced from 20 to 2 pieces, so easier to assemble. The flexible material is less likely to break, easy to replace if necessary, resulting in reduced maintenance, and again, it's lighter and cheaper to manufacture. This is an application from Genesis, custom grip for each single part. So custom parts every single time, printing in Ultem, ASA, Nylon CF, design freedom from AM, and then allowing repeatable and customizable parts. Engine parts can free up CNC machines. So for production parts, rather than machining the fixture, you can directly print the fixture and the jig to free up the CNC, and then you can obviously machine the part that you want to machine using the FDM polymer substrate. It's great for obsolescence. So metal parts can be replaced with Nylon 12CF. It's 3 to 7 times lighter than Ali or steel. Could withstand 1,000 bar of compressive strength. And again, it can be faster and cheaper than machining. You can print form tools. So this is an example from Safran, forming 1.6mm aluminium, 500 parts possible off a single tool. You can also form titanium, so that's a 0.5 mm thick titanium part. The tool has no finishing or coating required on the tool and can still withstand 500 parts through a cycle. You can print for aerospace. So Boomsonic print hundreds and hundreds of drill jigs, fixtures, assembly jigs, but you can also directly print functional prototypes as well as flight parts, specifically in ULTEM 9085, besides the certificates for aerospace for in-cabin use. This is an example of Antero 840CN3. I know it really rolls off the tongue, that name. Stratasys have got some strange names. This Antero is used by Lockheed Martin for deep space applications. Antero is a PEKK with carbon nanotubes. So it's an ESD safe with high chemical resistance, ultra low outgassing, and with high mechanical thermal properties. Directly for space applications. It's also the strongest material Stratasys offer in the portfolio. So a quick summary of where FDM is. Basically, yes, it's great for prototyping. I still use it for prototyping on small little hobbyist machines. It's great for PLA, quick, simple geometries. But what we've seen in developments is the composites. Which has opened many, many more applications like CMM fixturing, so really stiff components, form dies, even production spare parts using FDM. Switching technology, next PolyJet, the world's leading full-color multi-material system. So not poo-pooing SL or SLS, but if you're doing packaging, it was a single material color. And then if you wanted to do a full color packaging, you would then have to glue or stick or paint the SL or the SLS. What you can now do is able to print directly from design from rendering software like KeatShot, and then import directly from with a 3MF file imported directly into GrabCAD. So this is a nice example. This is a bottle that was printed in 8 hours, 20 minutes to wash the supports, and about 45 minutes to polish, either via wet and dry, or you can use a polishing wheel at low resolution revs. But yeah, that was printed. I'm still blown away that that is actually printed with the water droplets and everything. So PolyJet allows you to print thick transparent plastics, thin transparent glass, solid colors. There's 500,000 Pantone reference colors available. You can print stained glass, spray paint mask and clear sections directly printed. You can pad printed labels you can print, glue labels you can print, shrink sleeves, liquids, or you can really show off and print all the previous in one. Sorry, just skipped a page. So you can also mimic natural materials such as wood and fibers in the top right, but you can also produce complex, high transparency, full color 3D packaging with 2D graphics and labels all in one print. So what you can see there on the left was printed in one print. You can also print on fabrics. So using the fabrics add-on, you can print on cotton, suede. You can even print on nets. So this is printed with PolyJet few layers first, so a couple of 100 microns first, laying the net down, and then continue to print to produce full 3D printed nets. And this one of my favorites with full flexibility. I love this one. So further examples of applications with the fabrics printing, you can print consumable wearable electronics, again, pausing the print, adding electronics, continue to print. Concept car interiors, I know a few automotive are discussing production with PolyJet, and of course fashion, and again with production with PolyJet in fashion. Medical applications with PolyJet. So bottom right, you'll see blood vessels. So this is gel matrix used to produce fine vascular structures down to 1 millimeter internal diameter and a 1.5 millimeter wall thickness, simulating actual blood flow to replicate healthy and diseased tissue. So as you can see, it's a bit of a small video, but you can see the blood as it comes through, and that's actually flushing out the gel support. There's a material called tissue matrix. So tissue matrix is the softest material, I believe, in 3D printing at 30 Shaw 00. So around the gel shoe insole, as a kind of comparison of how soft it is, it's significantly softer than the original Agilus material that we have on PolyJet. The reason why it was developed is tissue matrix can be used to replicate heart tissue and tactile feedback that translates to clinical test cases. So it feels the same, it cuts the same. So it's more of a direct comparison to surgery. So it's great for either practicing for students or actually doing an MRI, printing the patient's heart, practicing before you actually do the surgery. So PolyJet, to summarize, can print visual anatomical models, full color. It can print functional anatomical models, so behave and feel like the real thing, in flesh, fats, bones, connecting tissue, skin. It's great for concept verification and design validation, although I would probably do SL for pure transparent. It takes a lot of polishing PolyJets for transparent parts. But you can also do functional performance. It's up to 7 materials printed at the 7 times. So you can do multiple assemblies as a digital mix. But again, because of the polymer science for PolyJet, functional question mark, yes, for fashion, but not actually full functional for production, like in an automotive application, under hood, that type of thing. No for PolyJet. Switching technology, Origin P3. So this is out of California. Stratasys acquired them, I think, about 2 years ago. This is DLP printing, but how it differs slightly is Origin produce basically they control the build sheet. So it's controlled and created a bit of a curve. So you have really low separation forces, which creates really beautiful surface finishes and really accurate parts. And you can also print incredibly flexible resins, which on most DLP you can't. Because of the separation forces, you'll get deformities as you separate. So a couple of examples, let's the Marek applications. So this is Loctite 402. It's great elongation at break at 230%. Good tear strength, especially against PolyJet, with a number of Shaw values available. It's also, because it's DLP, it prints a lot faster. Henkel Loctite 3955. It's one of my favorite materials so far that's come out. It can be used for aerospace. It's got UL 94 V0 flammability rating, 300 degrees heat deflection temperature. The only downside I found with playing with this material is elongation at break at 2%. So it's not great for anything that moves, as in clip features, living hinges, obviously, but static parts. This is for a design study for the F-16. So it's a hydraulic clamp for the F-16, and they could print 20 parts on the build in about 45 minutes with over 12,000 parts a month if you wanted to take it to production. Automotive interiors, exteriors under hood, sorry, you can do BASF ST45 is great, Loctite Indy 403, good, tough, durable materials that can be used in production. Again, question mark on certificates for these applications, but it's coming. Another tough application is Loctite 3172. I really like this material because of the elongation at break. It's got 108% elongation at break. So that one's been bent on itself and it still returns back to its original form. It's great for replacing HDPE or impact modified polypropylenes. This one's a robotic leg. You can print in biocompatible materials. So Loctite 412 is a great alternative to ABS, and it's biocompatible to ISO 10993, so it can be used within medical applications. It's also incredibly smooth. It's a really, really nice material to print with as well. The Loctite 9355 is quite tricky to print with. This one's a lot nicer to print with. So to summarize DLP, you can print housings, connectors, T connectivity. They're running their origin directly for production for connectors, clamps, injection molds, small little molds, medical components, gaskets, and especially handles, anything with long elongation at break, it's great for. Switching technology back to Andrew's background, it's Stratasys Neo. So the Neo range of materials, I'll cover a few of the materials. So Watershed XC, I was using this back at Materialize. It's a brilliant engineering material. It's clear with polycarbonate-like properties, highly versatile for general engineering. But what I see it most is vacuum casting patterns and prototypes. The heat deflection temperature is only 50 degrees, so it's very much more for prototyping and patterns rather than actual end use parts. Somers Perform. This is a fascinating material because it's ceramic filled. It's got a high heat deflection temperature, tensile modulus of 10,500 megapascals. It's predominantly used in Formula One and aerospace for wind tunnel testing because of the stiffness, but it can also be used for tooling because of the exceptional sidewall quality. You see the part top left, that was a glass filled with 70. It was glass filled polycarbonate with 70 shots at 150 degrees. Yeah, it can be used for production. We've got Sonos Taurus. This is more of kind of a happy medium between resins. It really can be used for production parts. It's got a heat deflection temperature of 91 degrees. It's great for ducts, HVAC systems, clips, fixtures. So you can do proper clips with it and it won't break. Manufacturing aids, but I know Toyota developed this material and we're trying to use it for production. Somers Watershed. This is a clear investment casting material, and then using magics, the tetra shell, as you can see here, resulting in low ash burnouts for casting. So it's specifically designed for the casting, so investment casting industry, producing beautiful masters, so highly accurate, fast build speed, and because of the tetra shell, as you can see here, incredibly fast burnout with very low ash. So to conclude on SL, a few further industrial SL applications. I've highlighted the most common in blue, mainly for prototyping, but there are some production applications, especially as the resins continue to improve. And then finally, introducing SAF, so selective absorption fusion. So you should see this video running. So this is two sleds printing in PA11 or PA12. So SAF is with the inline architecture with two carriages enables recoating and relatively cold powder while immediately heating. The advantage of this is SAF allows higher nesting densities compared to competitors. So we can go up to 15% nesting densities as standard, which speeds up volumes of print while not affecting deformity. So controlling the heat, basically. Great applications for SAF, so the HD50 PA11 moving parts. PA11's great, has a really high yield, so it's great in pack strength. PA11 is also sustainable. It comes from castor oil rather than dino juice. So PA11 long term, I can see really great applications if we, especially for any companies that are really focused on sustainability. You can print moving parts, quality durable parts, robust, and even bulky parts. Because of the controlling of the heat, you can print things like jigs, fixtures, brackets, which should struggle on other powder-based systems. Automotive components like side mirrors, air ducting, electrical cabling clips. And when you remove parts, you can automatically clean them. So we use the Dimension PowerShot C, which is basically glass bead blasting to clean the parts off. You can then dye the components. This is Dimension DM60 that automatically dyes parts. And you can take it a stage further, and you can shot peen. So that part is being shot peened and dyed via the Dimension PowerShot S. So DM60 to dye, and then the PowerShot S to shot peening. And then finally, with selecting the right technology for your application, cost plays obviously a pivotal role. So using the camera housing as an example, top right, I've highlighted the rough cost per part per build on each technology. So what's interesting for AM is P3 and SAF costs are actually quite competitive to injection molding depending on quantities, especially when you take into account the tool costs. A number of companies are adopting SAF and P3 because of the part costs. When they take into account the tool is actually competitive, and obviously it gives them the design freedom going forward. Okay, thank you. Hopefully that covered very briefly every single range. I could go in for hours on on Stratasys range. It's nuts. So I'll just stop sharing this slide.
Thank you very much, Martin. As before, a virtual clap for the end of your presentation.
No worries, thank you.
Fascinating, actually, to see so many different applications of the different technologies.
It's nuts. I struggle to keep up with the amount of applications you can actually apply across the board.
That was going to be one of my questions, actually, but I see we've got a hand up from Patrick, so I'm going to hand over to him first for the first question. As always, if anyone has questions, pop your hand up virtually or pop them in the text chat, and we'll keep an eye on both.
Thank you, Martin, for the nice presentation. I mean, it's been great to see the full range of applications that is possible. I want to ask you, where do you see design contributing to the development and dissemination and further uptake of this technology? You know, we are seeing a great increase in the application and real world cases. And where do you see design can move this forward?
It's like what Andrew talked about. It's the polymer science. So it's that I know Stratasys are going to bring out some better polymers on PolyJet in the next couple of years to make them better impact strength, better stiffness, and we're already applying it to things like fashion for production. So it is possible to use polymers in production. What we're also seeing is, especially on the FDM side, is getting the certificates for aerospace. That took a number of years. That's got all the ISO standards for aerospace. So we're now seeing that directly used in production on aerospace. And we also have SOLAS, which is seawater certificates to use in the marine industry. So ASA and nylon carbon fiber have all got the SOLAS certificates. So really doing having them in UV applications and seawater, and then doing lengthy testing on them to show that they actually last within seawater applications, which really kind of pushes the boundary of what AM can do.
Thank you. Thank you, Martin.
Thank you. We have another hand up from Parser, if you want to ask your question.
Thank you very much. I really appreciate, Mr. Martin, for your detailed explanation.
No worries.
Yes, the question that I have, what actually attracted my attention was the PolyJet machines that were used, and they were capable of printing colors too. And as a person who am a little bit experienced in the field of 3D modeling and also texturing, my question is that all of these machines are approaching to create a 3D object from the beginning.
Yes.
Were there any actually effort to break down the 3D model into a 2D or a plane object? For example, if we have a cube, into 6 actually squares, or even more complex actually object, because even for the texture in an object, we have to break down the object into a 2D plane actually design so we can apply the textures. Same thing, same thing happens to the 3D object, and the machines print this 3D object as a 2D shape, and after that we assemble it or bend it
You
to
can
make.
do that. You can print directly onto on the PolyJet. You can actually print directly onto a polycarbonate sheet if you wanted to, or you could print directly the model in 2D and almost like an origami, put it back together again. But you can also, it's because you can import as a 3MF file, you can print texture, color all at the same time. So you're importing the bump map basically from renders. So you're basically directly printing from the render, importing the color and also the texture, and the printer will then slice that as a bitmap and then print everything together in one. So there's 2 ways of doing it. You can actually, yes, you can print flat and then assemble, but you can actually print everything at the same time.
And does this and does this affect the speed of printing and the cost that of the actually the product in the end? How does it affect?
Sorry, say that again.
How does these 2 different approaches in creating an object, printing an object, how does this affect actually the price and the speed of printing? If we printed 2D, wouldn't it be faster?
Yes. If you print 2D, it's always faster. Every 3D printing is limited. Speed is always Z. If you print flat parts, it's quick. Everything tall in Z, 3D printing that's where your time is. So yes, if you print, that's why printing on fabrics is incredibly fast. So you can actually print a 500 by 400 in about an hour, full color onto fabrics. So we are seeing companies actually take fabrics, for example, into production because the speed you can actually print because of the low Z height.
Thank you so much. I really
No worries,
appreciate
mate.
Thank you. So we have time for. We've got 2 questions in the chat. I'll see whether you can answer them very quickly, but I'll go with the first one from Riaz. Do you see issues with regards to consistency of quality when you're mass producing items, especially when we're looking to manufacture to tight constraints design-wise and technically? Riaz says this is one of the biggest issues with the introduction of AM methods to the nuclear industry in particular due to tight constraints and safety implications.
Well, what we do on SAF, for example, we especially for production parts, is you print the parts, but you also have dog bones printed within the nest. So you're printing dog bones in all the different orientations, and then you tensile test the dog bones afterwards for that batch of parts. So you can really ascertain that you know that those parts in that cake conform to the application. You can also apply WAM. So basically on GrabCAD Print, you can print a component and then do a 3D scan of the component, bring the scan data back in, and it will then analyze the part compared to what you printed. And then GrabCAD will then change the component so you can then get in more accurate parts the next time. And that's another way of really kind of pushing AM into production.
Fab. Right, I'm going to give you very quickly the chance to answer the last one because I think it's an interesting question. So Stefano has said, thanks for your presentation. Do you have any direct experience about FDM materials resistant to non-neutral liquids such as cutting oils? So particularly for things like grippers and automation.
Yes, there's a couple of ones that are rated to well, basically good for kerosene and diesel, and they've got the certificates that they're absolutely fine. So Ultem's a good one, 9085, that's absolutely fine in those applications. But also nylon CF10 we use in CNC machines, and a lot of them have a lot of nasty oils that are going through, and we don't see, because it's nylon as a base, it's absolutely fine. So yes to the answer.
Wonderful. So thank you very much, Martin. Super interesting to see all those different applications.
Yeah, it was a
and
lot
to
in one.
consider.
Sorry.
I think that's fine. I think that sort of thing really generates thinking and gets people really kind of understanding some of the variation in what we can do with AM. So that's excellent.